Yeah. Hello, my name is Yasuyuki Tanaka. I'm engaged in vulnerability and malware analysis at NTT-CERT. Today, I will talk the title, Comprehensive Investigation Results on Malware Code Interpretation by GPT-4. So let's start. So this, motivation for our study. The first one is how effective is GPT-4 for malware code analysis. Actually, what behavior can GPT-4 understand, and also what behavior cannot GPT-4 understand? We would like to know the detail. The next one is there are some issues from existing research. We think there are not enough dataset that covers all typical behaviors. And also we think there are not enough dataset that answer can be checked because LLMs, occasionally produce hallucinations. So yeah, our proposal method, we decide to evaluate the kappa rules, hit function as the correct answer data. Kappa tool developed by Mandiant that detects typical malware characteristic using rules. We also use kappa on our daily analysis works, and its rule is reliable, we think. So we choose this method. First I explain the setup. We use Ghidorah to obtain the decompile and disassemble code. The second, we use the kappa rule to obtain the target function address and put label according to the kappa. So in this picture, label is RC4 KSA algorithm. So example. So after that, attach the prompt to the function and query to the GPT-4. So finally, after we get a result, we checked its result is correct or not manually. This slide shows other experiment setup. This experiment, our target is P file, and we use GPT-4o in that time. GPT-4 queries for the compiled code, DC code, and DA code are performed independently in this experience. And we also use these simple prompts in these experiments. Okay, research questions. We set up 3 research questions. The first one is behavior identifiable through the compiled code and its trend. Actually, these days, the compiled technology improved rapidly, so it is very accurate. So with the compile accuracy, our first option to malware analysis on daily basis. So RQ1 is important. And RQ2, behavior not identifiable through the compiled code and its trend and improvement strategies. We feedback improvement. We aim to enhance future utilization of the GPT-4. And the last one is RQ3, behavior identified through even disassembled code and its trend. This is the category and inspection items. From 35 category and 273 items from AV anti-debugging and the actually detailed slide. So we try to enhance coverage of category. Okay. So this is the overall result. Overall result on each category. So in DC means decompiled code. Decompiled code, 70% was identifiable totally. So only 70% identifiable on the decompiled code. On the other hand, in DA means disassembly code, 8% was identifiable. Also, this each category, orange category means high percentage category. And these behavior is behavior seen in normal application as well as malware. The green means low rate, low percentage category. And it includes very malware-specific behaviors, especially in the using immediate value or using a specific flag or some injection approach or multi-step operation and the difficulty in identify the intent. The last one is the purple. Purple is a means category that even disassembly code were identifiable. Okay, I will explain some example. So this example is behavior identifiable through decompiled code. The category is anti-AV. So this code means disabling event logs. So by examining the loaded address of, in this case, it is our event write Windows API function and overwriting the beginning of the corresponding address with 0xC3. It means return. So finally, event log is effectively disabled in that case. So GPT-4 also explained well in the bottom. Okay, this is the not identifiable through DC code. Also, category is anti-AV. It code means the changing process mitigation policy. And firstly, it guards against DLL injection by changing process mitigation policy. While the update to the process attribute list using update proc thread attribute API is understood by GPT-4 in this case, but the meaning and the effect of the attribute value remain unclear by GPT-4. When the setting 0x to 0007, it means proc thread attribute mitigation policy. It restricts DLL injection to only those signed by Microsoft. So red character means important. So okay, final example is the behavior identifiable even through the disassembly code. This assembly code is hard to understand. So this is the encryption category, RC4. So first, I explain the key scheduling algorithm, KSA features identified by human analysts in decompiled code. Actually, KSA has a SBox permutation, initialization and SBox permutation based on the key. Also, there are two 0x100 loops and mod 256 operations. This is the GPT-4 result in decompiled code. GPT-4 identify also KSA based on SBOC initialization and SBOC permutation, just like human analysts. Finally, this is the GPT-4 result in disassembly code. GPT-4 also identify KSA based on SBOC initialization and SBOC permutation, but it's a disassembly code, even in disassembly code. Okay, I explained the result. I explained the sample. So we have conducted this type of analysis of all items due to the large volume research data. So I will explain the summary for each research question after the session. Okay. So yeah, research question 1. Behavior identifiable through DC code result. I summarized each category of result. So also you can see the legend. Red letter means for malware specific method and logic. And green letters means for Windows related specification. Yellow letters means for some algorithms. This slide shows from the anti-AV to the encryption AES. And this slide also shows the result of RQ1 from encryption RC4 category to the process general category. So you can see the also color. Okay, this slide also shows the result for RQ1 from process injection category to the persistent category. So I cannot explain the details, so you can see the slide. Okay, so based on this research, we find some finding. So I will explain the finding 1. So finding 1, GPT-4 is capable of explaining code that involves relatively well-known techniques or has clear inferable intent, including anti-analysis, infection activities, and persistent mechanism. There are 3 points. The first one is the common techniques or specifications are widely known method often seen in malware. Things like process harrowing, they are well documented in research and analysis blog, even if not officially part of the API, Windows API. The second one is inferable intent. It refers to the techniques where the propose isn't immediately obvious, but we can guess it from context. A good example is inserting ZXC3, I explained, to silently disable a function. The last one is clear intent. It means the behavior is easy to understand at a glance, like creating mutex. Even with multiple APIs or command, the goal is clear. Okay, finding 2. Finding 2 is green, so related to Windows. GPT-4 can understand Windows APIs, well-known argument, and other Windows specification, allowing it to explain many typical behaviors of malware. There are 3 points also. Knowledge of Windows API. It helps identify behavior just from API names in the decompiled code. This includes typical techniques like anti-debugging, anti-forensic, process injection, and also shellcode loading, and persistent mechanisms. And the second one is that there are knowledge of API arguments and how they are resolved. This focus on how arguments are used in the code, infer intent. So there are two patterns. In pattern 1, critical argument appears as immediate value. For example, calling HTTP query info with 260.5 clearly shows it's trying to get the context length. In pattern 2, arguments come from stack variables that point to specific strings, like executing a command with shell execute command. So yeah, last one is the we include other Windows specific knowledge, such as detecting CPU count using WMI queries. Okay, finding 3, GPT-4 can identify well-known this is algorithm. Yeah, logic for checksum, encryption, and hashing. GPT-4 identifies these specifications, such as CRC32, AES, and RC4, especially in terms of constants and algorithm features. Okay, let's talk about the RQ2. RQ2 is not identified through DC code. I also summarized the each category of result. Also, you can see same legend. I say again, red letter, malware related, green, Windows specific. The yellow is some algorithm. So also you can see the summary result from the some category. So this slide also show result for not identifiable behavior from the encryption to the process general matter. So you can see, I'll skip. So this slide also shows the result from process injection. Process injection, yeah, related to let behavior, you can see, actually, to the targeting category, yeah. Okay, let's talk to the finding. Okay, finding 4. GPT-4 is unable to explain, sometimes unable to explain to code involving anti-analysis, infection activities, and persistent mechanisms when the technique are relatively unknown or when the intent is unclear or difficult to infer. Yeah, also I will explain the 3-point. Relatively obscure technique or specification. It refers to methods that might show up in niche blog but aren't widely recognized or discussed. They are not part of mechanism detection knowledge. The second one is we have difficult to infer intent. In these cases, the code itself looks simple and understandable, but it's hard to tell what the malware is actually trying to achieve with it. Finally, unclear intent. Unclear intent means that even through each operation in the function is readable, the overall goal remains ambiguous when we try to piece everything together. I will show the example. This is the example from finding 4. the Windows copy file to function has an optional parameter, such as on the display's progress. GPT-4 only interrupts this as a file copy operation. It does not understand that shellcode is being executed using the copy file to. Actually, this region contains the shellcode, and it is executed as a callback function through the third argument of copy file to. And also, this is the example for finding 4. So this is a technique, some process injection technique, extra Windows memory injection, which similar to the other method, and where the intent is difficult to determine. This includes some 5 steps. Yeah, actually, I don't explain detail, but the 5 step is necessary to this type of injection. So in that case, yeah, actually GPT-4 provides the individual explanation for each step, but it does not address the overall result of the combined operation. Okay, finding 5 are Windows related. They sometimes reach incorrect conclusion because it does not make judgment based on accurate argument resolution for Windows API. The first one is the knowledge and resolution of Windows API argument. When the API argument is given as an immediate value rather than a reference, name resolution doesn't work as expected. As a result, semantic interpretation can fail. This isn't just a rare edge case. In fact, we found these issues appearing across 7 different categories, and it affects 11 specific inspection items. And the second one is the errors in understanding Windows API argument. I will explain the next slide. So the last one is limitation. Lack of COM object identification and related limitation. GPT-4 is unable to resolve COM object name, and shoes cannot interpret the intent. However, since this is an issue on the decompiled code side, I think, it is excluded from this finding. Okay, I will explain the previous example result. So in this code, we use the CryptoGen key API. In CryptoGen key API, the algorithm is determined by the second argument. So second argument is important. In this case, it is actually a yes, but it is mistakenly determined to the triple death. On the other hand, it correctly determined major constants, immediate constants, such as HTTP query, context length I explained. GPT-4 is unable to correctly identify certain compression algorithm and some hash algorithm, or it misjudges them. GPT-4 identifies MD5 SHA algorithm based on bitwise operation and round structure, and also initiate hash value H, unique constant K. GPT-4 misjudges SHA-512 as SHA-2546. GPT-4 is unable to identify SHA-224. I will explain the next slide. About initial hash value H, SHA-224 and 384 share the same row numbers. And also 256, 512 share the same upper byte. Also, about unique constant k. 224 and 256 share the same constant. Also, 354, 512 also share the same constant. Yeah, it is specific. Yeah. Okay, final research question. Behavior are identifiable even through the DA code. This is the behavior identifiable through IIA. So you can see some method and logic and algorithm. You can see that slide. Okay, finding 7. GPT-4 can identify anti-analysis technique that evident at the assembly level using PEB, process environment block specification, and x86 interaction specifications. The example is some debugger detection or find the stack string techniques. This is the last finding. Finding 8, GPT-4 can identify well-known checksum encryption and hash algorithm at the assembly level using constant and algorithms. You can see the CRC2, AES, RC4, or something like that. Okay, final topic, improvement strategy based on research question 2. Based on finding, we devised an improvement strategy. For finding 4 and finding 6, we've made lag and prompt improvement. For finding 5, we've made converting immediate value to name. Lag and prompt technique is not so special. So I will talk about topic of converting immediate value against the finding 5. Yeah, to begin with, we use LLM, also ChatGPT-4o, to identify potential macro names that correspond to immediate value found in code. The process involved a few key steps. First, we extract lines from the compiled code that reference Windows API function. They are often rich in context, constants, and parameters that we want to analyze. Next step, we use the method to interpret the argument in those API calls. For each argument that includes an immediate value, the model suggests possible macro name that might represent those values, things like predefined, constant, or flag. It's worth nothing though that the model suggests aren't always perfect. Sometimes the suffix in proposed macro name might be incorrect. This is something we keep in mind when reviewing its output. But in our experience, sometimes suffix of m is incorrect, but the prefix of m is always correct. So, okay, so the prefix is correct. So let's use it. Assuming the prefix is correct, determine the suffix correctly with 3 functions. Number 1, macro name expansion database. It is a conventional forward situation database from macro name to immediate value. Number 2, prefix candidate generation. Generate P, it means macro prefix from the small m, candidate macro name as shown in the figure. Number 3, with LLM with LLM, using LLM, macro name selection and macro name calculation function we prepare. There are two cases. One is where the one macro for an immediate value, and the cases where there are multiple macro as macro names shown in this diagram. So, yeah, this is the improvement result. With this improvement, the compile identifiable rate from 70% to the 86%. But there are two things we couldn't improve. The one is some algorithm. Yeah, I think resolution, in addition to fixed value, the system have the run LZO characteristic processing. The other is match PEB-related thing. So there are two resolution, we think. Extend the name resolution of immediate value that I explained to perform the name resolution for offset value from the PEB. Resolution 2, interpretation in assembler code. Especially the offset value remains the same unless it is intentionally modified by calculation in assembler code. Also, there are some techniques that can only be detected in assembler code, such as Hebb's gate. So there is worth considering this. OK, finally, time's up. So this is the last slide. So summary and takeaways. So yeah, do you have any questions?
So if any question, please step up to the mics.
Actually, we set the three research questions, and this is the result. So you can see the result.
Excellent. Thank you.
Thank you. Thank you very much.